and Q-learning, which both use one-step bootstrapping. So they use the value, they use an approximation of the value that is computed with the same action value function. And the difference between the two algorithms is that the target function for one, for SARSA, is computed using the current policy, and the other one with the greedy policy over the current Q-value function. But you can see here in that case, we introduce the parameters W, which is basically the weight of the neural network. And that's because, well, those are the weights of the deep neural network implementing those Q functions. So the generalization to deep neural networks is pretty straightforward. So the main idea is that we want to approximate the true table, which is unknown because potentially too big to count. That is QSA. And we want to approximate it with a neural network that takes into input state and action. This neural network is parameterized by its weights, and we output an approximation of this value for each state action pair. In practice, especially for images, you want the recording has stopped. Maybe we should restart it. No, if you want to. Okay, I don't know why the recording has stopped, but okay. So first we need to, as I said, map the states to a representation, some feature vector that is have some dimension h, and then we apply some nonlinear transformation, hyperbolic tangent, ReLU, and map this hidden vector to the M action values. So there are two possibilities. Either you only process the states and then you have n outputs to your neural networks, one output for each action. So at every time you compute all state actions values, because you have n heads to your network, or you give both state and actions to your network and put a singular value. This might be more practical, especially when you have a lot of different actions, still discrete, but you don't want to bother having a lot of outputs every time of your network. So this is a very simplified version of the reinforcement learning loop. But in the case of Atari games, the action is, for example, is controlling the little character with some up, down, left, right actions, some jump button potentially. There are some other actions depending on the controller. The reward is basically the score in the game, and the state is the image you see on the screen. So it is straightforward. And so how does the network look like for this? Where in this case we have end-to-end learning of the Q values from the pixel S. And so you could imagine that, for example, the first three layers are actually first two convolutional layer. Here implements the feature representation that we talked about, and then after flattening, you have some vector, and then you have the last two fully connected layer on this image that implements the Q value function, for example. And so in this network, we input the state S, and we don't only input the image currently, but we input the last 4 frames. Why? Is because if you think about it, only putting one frame misses some information. And why is that? Does someone have any idea why? It's very critical in a lot of environments to either do this, which is concatenate the last 4 frames or n frames, or use a recurrent neural network.
The different frames are from different timestamps?
Yes, the previous ones.
So it's just some history information, like some dependence between them?
Yeah, and why do we need a history?
Why?
Probably because of the characteristic of this particular game, that their history depends on your future movement, like where that, I don't know, that pixel come from, the direction or something.
Yeah, you are getting there. Imagine it's just a very simple game where there is no long-term consequences, just short-term. For example, imagine if it's Pong. So the two bar, and that is the ball that goes in between. What's the problem if you only take one frame as a state? Why do we need more? Why do we need the last frame?
So you need to know history to know how the ball moves, like where it comes from, which direction it moves. Otherwise,
and what is it called in a more formal term in reinforcement learning? We saw that in the first course. It's called partial observability. Remember, if we only take one frame, indeed we don't have the speed nor the direction of the ball. So actually, we don't know where the ball is going to be next time step. We cannot even make a guess because we have no information about the speed and the direction. So we'll actually lack information to define the state. And that's why in the Atari games and in a lot of other environments, we just concatenate the last 4 frames to include direction and speed information that is not contained in the static image. And that way we can recover the MDP. Otherwise, we are in the POMDP, and the algorithm are not will have a hard time converging because they are designed to work in MDP. The reward is the score, and in this case, it's a choice, I guess, just for practical reasons. There are many games, like between 50 to 200 games. So they decided to keep the network architecture and hyperparameters the same, which is a very reasonable assumption. Yeah, you don't want to adapt the architecture to every single game. In the end, you don't want to reinforcement learning to just play video games. So it's not interesting to try to overfit to this. Okay. So when we have a value function approximation. Yes.
Regarding the 2 options that you provided before for the output layer, can you repeat them and also relate to this example, to the architecture in Atari?
Yes. Okay, good question. So the 2 options were either here in this case, for example, you only give the state, which is the last 4 frames. And then at the end, you don't have one output, so you don't have one scalar, but you have like n values, each value for each different possible action. So for example, if you're in a game where you just move around up, down, left, right, you have 4 possible actions at every time step. And so your Q-value network will output 4 values, one for each state and action. So you input the states, and then you just output 4, one for each action. So it's kind of like you can think of it as a classification in deep learning, where you have n classes and you need to choose one. That's the same architecture. Other possibility, and that is what is used. That can also be used, especially if your action cannot be counted or are continuous. Is that you input the state to the neural network, and then in the middle, for example, before the first linear layer, in the middle, you also concatenate to the feature vector. You concatenate the actions, the action vector or action values. Action vector, and then you forward this to the last layers. And so that way, it's as if you have a function that takes as input both state and action, and then at the end you have a single value.
And what does that represent? And what does that value represent?
And the value represents the Q value of this state action pair. So remember in the last lecture, our Q function was just a table where the rows were each possible state in the environment, and the columns with each possible action. And so for each state and each action, you have a particular value, which is by definition the expected discounted return that you will get if in this state you take this action. That's the definition of the Q value. And so that's what we are trying to learn. That's the whole purpose of the course. We are trying to learn this Q value and then use this Q value to control our agents by, for example, following a greedy policy. Is that more clear?
Yeah, so we got, at the end, we got expected reward, right? Which is in a Q table. Or
we don't have tables anymore because, as I said, you could have a table when you could count the states, but here you cannot count the states. Each image is a different state, and so the number of images is exponentially large. You cannot count. You cannot assign a table with like an infinite number of rows because you have an infinite number of images. That's the whole purpose. You need a function that computes it for you. So you don't have a big table anymore that stores the value for every state. You have a function that approximates the tables. But that is the same in any deep learning case.
yes.
If you think about it, for example, if you want in deep learning to learn a function that, for example, that gives you the true true buying price of a house in Paris based on the multiple factors. Well, the problem before talking about deep learning, you could just view it as you have a big table. For example, let's say there are like two parameters. I don't know, location and size of the apartment. Well, then you have a table with all possible sizes, all possible locations in Paris, and you have a value in price, a price for each those values. Okay. Well, in practice, the number of locations is infinite. I mean, you can place your house wherever you want. It's continuous, and the number of sizes also. You are not going to discretize between 0 and, I don't know, 200 square meter. So you could, and that's like a very basic deep learning problem. You want a neural network to approximate this big table and take as input size and location, and output a value. And here is the same. It's because we cannot count the states anymore. So we have a neural network that takes as input states and action and outputs a value. Is that more clear?
What does the reward is changing score for that step? What does it mean?
Sorry?
The reward is changing score for that step. Like how it's related to the neural network.
It's exactly the same as in last course. It's just that now when we update, we don't update a table anymore. We update the weight of the function. We update the weight with the gradient descent, but the update looks exactly the same.
So the score, what is the score? The score is the V value?
Okay. In Atari, the score, the reward is the score of the video of the game. It can be, in other problems, it's not the same. But when you play a video game, what you want is have the highest